Welcome to the work and energy topic. In this topic, we'll start working with vector multiplication. So, welcome to vector algebra part 2. There are 3 types of vector multiplication. The first of that is the multiplication of a vector by a scalar, so by a number. That gives us a vector, and that is called scalar multiplication. The second type is when we multiply 2 vectors together and we get a scalar. And this is known as the dot product because it's always written using a dot, or also as the scalar product because the result is a scalar. And the third type is again multiplying 2 vectors together, but that gives us a vector. And that's known as the cross product for reasons that you will find out in a later video in a later topic, or the vector product because it gives us a vector. So scalar multiplication is when we multiply a vector by a scalar, so just by a number. And in this case, we multiply each component of the vector by that scalar. So I've used a 2-dimensional example here because it's easier to draw, but I will give you the formula in 3 dimensions. So if we have our 2-dimensional vector, 3i plus 4j, we know that the magnitude of that vector is equal to 5. And if we multiply our vector by 3, we just multiply out each component. So our result is that 3a equals 9i plus 12j. Which looks something like this. And the magnitude of our new vector is equal to the square root of 9 squared plus 12 squared, which is 15, which is 3 times the original vector. So when we do scalar multiplication, the magnitude of our vector changes, but the direction does not. So the general formula for scalar multiplication of our 3-dimensional vector A, we just multiply each dimension individually. So c times our vector A is c times the x component plus c times the y component plus c times the z component. Our second type of vector multiplication, and the last one for this video, is the dot product. So here we multiply 2 vectors and the result is a scalar. If we take as an example our 3-dimensional vectors A and B, when we take the dot product of A and B, we work as we would for vector addition or subtraction, in that we work with each dimension or each component individually. So since it's multiplication, we multiply the same dimensions together and add them all. So we take our 2 x components and we get ax, bx. We add to them our 2 y components, ay, by, and then we add to them our 2 z components, az, bz. And the result of that is a scalar. So as an example, we take our 2 familiar vectors, our vector A, which is equal to 3i plus 4j, and our vector B, which is equal to 5i plus 2j. When we take the dot product, we multiply first our x components, so 3 times 5, and then we add to them our multiplied y components, which is 4 times 2, and that gives us a result of 23. So when we take the dot product of vector times a vector, we get a scalar. Geometrically, what we're doing is we're multiplying the projection of one vector onto the other with that other vector. So we're looking for the components of the 2 vectors that are acting in the same direction. If we take a simple case here, we've got a vector A with its x and y component at an angle theta to the x-axis, and a vector B which only has an x component. When we take the dot product, we get ax bx plus ay by. From our diagram, we can see that ax is equal to a cos theta, and by is 0. Which gives us that the dot product of these 2 vectors is equal to the magnitude of A times the magnitude of B times cos theta, where theta is the angle between the 2 vectors. So although I've shown this for what appears to be a simple case, this equation will hold for any 2 vectors A and B, because you can prove it, and when you perform the multiplication, you just choose the coordinate system such that the second vector will always have a 0y component. The dot product behaves very much like a normal number when it comes to a number of properties. So you can prove each of these by expanding out the equations into each of their components, but I will not do that here. So first up, the dot product is commutative. It doesn't matter which order you do the multiplication in, the end result will be the same. It's distributive, which means it expands out as would any equation in brackets. Multiplication by a scalar also behaves as expected. So it doesn't matter in what kind of formula you have your scalar. You can pull the scalar out the front, do the vector multiplication, and multiply that result by the scalar. So in summary, scalar multiplication just increases our vector magnitude by a factor, and the dot product multiplies two vectors together and gives us a scalar. And as with vector addition and subtraction, the key to both scalar multiplication and the dot product is to work with each component individually.